Okay, so I had reaction 10 for my, group 10 for my reaction video, and it's what I believe to be a nucleophilic addition reaction. At first, I tried to see how many steps it would take, and so almost immediately I noticed that whenever you have like a carbonyl or just that regularly bonded ketone, it almost always is gonna break off to form to make an alcohol or some other sort of bond. Typically with those, the double bond gets broken, but on this one there were two double bonds. There was one between the carbon to carbon bond here and the carbon to oxygen bond there. Since the carbon to oxygen bond is polar and the oxygen is a little bit more electronegative, it's going to carry more of that partial charge. The carbon to carbon is not necessarily, well, it's described as being a little bit more polar, but they're sharing electrons. So when those bonds break, they tend to not really do too well and are not really stable. That's why it's better for the electrophile, being that carbon there, it's going to want to absorb. Well, it's going to become electron deficient. So it's going to be the one that's absorbed in the attack, which is kind of shown right there. So this is the nucleophile. Kind of on the back is where I drew the entire reaction for it, for how they attack each other. And then starting off, I kind of did all my steps. So the electrophile is going to be that carbon of the unsaturated ketone group. The carbon is typically electron deficient because it's going to have a more favorable bond between carbons and hydrogens. But when it comes to the nucleophile, which is the lithium aluminum hydride, that's going to offer that extra electron that's going to protonate onto the oxygen and give you your jump over here. It said assuming acidic workup, so that's kind of where on the back I assumed it was good to have the hydronium, because typically the hydrogen will break off and then kind of go towards there. But then when I watched it, I noticed that it went to the bottom. So I started to think, okay, since once this dissociates, the lithium will be a little bit positively charged. And so protonation is going to have to occur with this one to be able to add to the oxygen with the valence electrons. So when I go back over here, I'm taking into account the electron flow. So the hydride ion is going to come from the lithium aluminum, since why its name is lithium aluminum hydride, sorry. But the hydrogen that's going to come off is going to be negatively charged. And we need a positively charged electron, well, a positively charged ion to go and then join up with the oxygen. So that's where I started to think, okay, so since once that dissociates, the lithium will have a positively charged one on it, but it'll just be like an electron to where like that's part of the leaving group. So I left that alone, and then I assumed for the acidic workup that we'd find the extra charge for the hydrogen needed to add on to the single bonded oxygen. So coming back over here, the regiochemistry is going to be in favor of the reduction. Well, regiochemistry is what the stereochemistry, I guess, form would be, because it's going to occur at the carbonyl group due to the breaking of the bond right here. You're going to have a nice electrophile. Nucleophile is going to be there. I got kind of confused when I did the workup, because typically in the homeworks and everything else, I can kind of differentiate between which one is which. Oh, sorry. But in this one, you got the benzene ring, you got the carbon to carbon double bond, you have the carbonyl. So what I decided was, per usual, whenever you have a sigma double bond that breaks, it's going to form your pi bond. So that's going to break it and form another one, which will be down here. So once those two break off, you're going to attract that electrophile. The nucleophile is going to attack right down there where the more electronegative carbon is going to be at, because it's going to need one to fill its shell. Then you come over here. So I have the negatively charged oxygen right here, hydrogen right down there. I assume the acidic workup, because one needs to break off that bond from that hydrogen, and then this oxygen is going to have to find a positively charged hydrogen ion. And typically with an acidic workup, a lot of water molecules like to form and break with some of these things, because hydronium ions are pretty much going to donate the proton to that oxygen. So that oxygen is technically still being from that carbonyl up there. I decided to take that and then add another reaction. Oh, the arrow, sorry. So I used the arrow from the hydrogen, form a bond there. This is going to break the bond there, send the electrons to the oxygen. Then you come over here. From there, you're going to have your new product. And you're going to come down here and think, in order to get to the final product, I'm going to have to add one more protonated hydrogen here. I'm going to have to break that bond. So what I did was, your acid is going to be your hydronium. It's going to grab the ion there. Well, the positively charged hydrogen from that group here, it'll break off, go to the oxygen, which will then break off that hydrogen, send that back there, and then you will have your final product. As far as that last hydrogen, I am assuming it could go back and reform with the hydronium again, or just kind of like leave it off and it would just return to water. And that's the only hiccup that I think I had, because typically whenever I do see it on the homework or I see those on Achieve, it's just kind of doing the two-step reactions and kind of figuring it out. And there's multiple chances on those. But since this one was kind of just me trying to follow the lines and then using the acidic workup and figuring it out, in my opinion, I think this is the best way to kind of illustrate the addition, breaking of the bonds, forming of the bonds with the arrows, and coming up with the final product.